Matrix matching. Column 1, column 2. This is the figure given where capital and small m is kept on capital M body. Between the surface and capital M, the friction coefficient is 0. Between small m and capital M, friction coefficient is mu. In the above case, the condition of no slipping between small m and capital M, we need to calculate. The four options are given as PQRS. F is less than or equal to mu mg 1 plus small m by capital M. And F is less than small m plus capital M into G. In the question number 2, again small m and capital M as shown in the figure. Same friction mu. In the above case, conditions of no slipping between small m and capital M is. The difference between these two figures is the capital F is applied on capital M and here capital F is applied on, or the force is applied on small mass. In the C part, only one mass is there, force is applied on it. In above case, the condition of no slipping is. Here, we are taking this as m root 2 mass and a force is applied on this mass. This inclined plane is fixed. In the above case, the value of F so that the small block can move up the incline. So, force is greater than 0.6 mg, force is less than or equal to m into mg. So, what we are going to do is, one by one we will take the cases and try to analyze when the force is on capital F, when the force is on small f, then small m, then what is going to happen. So, first case we will take small m, capital M, and the force is applied on capital M. Between the ground and capital M, coefficient of friction is 0. Small m and capital M, coefficient of friction is mu. We want to calculate the condition of no slipping between small m and capital M. What should be the maximum value of M? That means indirectly, we want to calculate maximum force such that there is no relative motion between small m and capital M. Correct? So, if we take the free body diagram between for small m and capital M, the situation will be as like this. This is capital. There is no friction between the surfaces. So, here you will have the friction force F1. This friction force F1 will be the force trying to pull this body forward. This is small m. This is an applied force. So, F1 will be equal to, if we take it, this is mg force. Normal reaction will be N1. Here, normal reaction N1. This is capital Mg. And here, this is the normal reaction N2. So, we know N1 will be equal to mg. So, friction force F1 will be equal to mu mg. Right? And the force here will be F minus small f1 should be equal to capital M into A. Second equation, F1 is equal to small m into A. So simply we can write F is equal to capital M plus small m into A. This is the acceleration of the system. This is the force applied maximum. So if there is no relative motion between small m and capital M, we can call the force maximum will be capital M plus small m, acceleration maximum. So first step we need to calculate the acceleration maximum. So if we eliminate the value of F1 and get the value of acceleration, acceleration can be written from here. If mass m should not slip, if I take this as equation 1 and equation 2. From equation 2. Maximum acceleration of small m for no relative motion between small m and capital. So I'll call this as A max. Friction force F1 is mu mg, mu small mg divided by small m. So it can be written as mu g. Now this A maximum, if I substitute, I'll get the F maximum. Therefore, F maximum force is equal to capital M plus small m into A max. Or we can write F maximum is equal to capital M plus small m into mu into g. This is the maximum force in the first figure. Likewise, we'll calculate for the second figure as well as the third figure and so on. Now B part. Now small m is above, capital M is here. Friction force between capital M and ground 0. Friction force between small m and capital M again mu. This time applied force is on the small m. So free body diagram. This is small m. This is capital F. Normal reaction N1. This is mg. Friction force here F1. Now this friction force will be an applied force on the below body. There is no force here. This is N2, this side you have N1, this side will be capital M. So one equation, N1 is equal to mg. So friction F1 will be equal to mu mg. Now applied force capital F minus F1 should be equal to m into A. Second, F1 is equal to capital M into A. So again, F is equal to capital M plus small m into A. Let me call this as equation 1, this as equation 2. Now, maximum acceleration of capital M for no slipping between small m and capital M. What we can do? We can calculate from equation 2. What we get? Maximum acceleration of Kaplan for no slipping between small m and Kaplan. So we can write A maximum from equation 2 will be mu mg divided by Kaplan. Substituting this value here. Therefore, F maximum is equal to Kaplan plus small m into A maximum. So nothing but Kaplan plus small m into what is A maximum? Mu mg divided by Kaplan. We can also write this, reframe it as F maximum is equal to 1 plus small m by Kaplan into mu mg. This is the force maximum. In the C part, force is there. Coefficient of friction between Kaplan and the ground is given now, mu. And what we need to calculate? We need to calculate in the above case or in this condition for no slipping is, for no slipping, F external should be less than or equal to the limiting friction. No slip. F external, correct, should be less than or just equal to the limiting friction force. So F should be less than or equal to FL. Limiting friction force is mu into normal reaction. And what is the normal reaction in this case? Kaplan G. So this will be F is less than or equal to mu mg. If the external force is less than or this, there is no slipping. In D part. Now the mass is m by root 2, theta is 45, this inclined plane is fixed, mu is given as 0.2. We want to calculate the value of F so that the small block can move up the incline. For upward motion, the friction force will be in the downward motion. The friction force will be directed in this direction. This is the friction force direction. There is one component of mg here. This is mg cos theta. Another component of mg here. This is mg sin theta for upward motion. Frictional force will be downwards. F minimum is equal to m by, mass is m by root 2. This is mass is m by root 2. Here also mass is m by root. M by root 2 into g sin 45 plus the friction force mu times of normal reaction. M by root 2 into g into cos 45. So F minimum is equal to, mu is given as 0.2. mg by root 2 into root 2, that's 2 plus 0.2 into mg by 2. So F minimum is equal to, now here 1.2 divided by 2, 0.6 mg. For the body to move up the incline, the force which should be provided will be greater than this minimum force. That means the force must be greater than 0.6 mg. Now let us look one by one what are the correct answers. First one. In part A, in the above case, the condition of no slipping between small m and capital M is F maximus Kaplan plus small m mu g. So correct option will be for A, F is less than or equal to mu mg 1 plus Kaplan small m by Kaplan. F will be less than or equal to mu m plus Kaplan into g. So we got it, F maximum should be equal to, so this Kaplan should be less than or equal to. So correct option will be option Q for option A. So for A, it should be Q. Similarly for B, in the above case, the condition for no slipping between small m and capital M. We got force maximum as 1 plus m by capital M mu mg. So in the above case, here we have to calculate F less than or equal to mu mg 1 plus capital M plus. So correct option will be P. So for A, it is Q. For B, it is P. Similarly, for C, condition for no slipping, mu mg. So it will be mu mg. So C option is S. And D option greater than 0.6 times of mg. So it will be greater than 0.6 times of mg. So what are the correct options or the correct answer? For answer A, it is Q. For B, it is P. For C, it is S. For D, it is R. So correct answer will be A is Q, B is P, C is S, D is R. This is the correct option for this matrix match.